Hi everyone, I am Felipe Toledo, and today I'm going to be presenting our paper Distribution Models for Falsification and Verification of DNN. I have worked on this paper together with David Schreiber, Sebastian Elbaum, and Matthew Doyle. Deep neural networks are increasingly being applied to safety-critical domains like autonomous driving cars or medical surgical robots. Therefore, there is an increasing need to verify these systems to ensure a certain level of safeness. In the last couple of years, researchers have developed different algorithms to determine if a DNN meets the specified requirement. Let me quickly explain what a DNN verifier is and how it works. A verifier is a tool that takes in a safety property and a DNN model, and outputs whether the property holds, is violated, or unknown. Unknown means that the verifier cannot determine if the property is either of the two other results. If a property is violated, most verifiers will also produce a counterexample to the specification. If our DNN deals with images, the property violation or a counterexample image may look like this picture. Now let me show you a toy example. The fashion MNES network is a model trained with clothing data to identify which piece of clothing each image is. The input of the network is a square 28 by 28 black and white image. In this particular case, it's a t-shirt. And the output is one of the 10 classes of clothing. In this particular case, it's a t-shirt top. As I mentioned before, to check the safety of these systems, it is necessary to check if the model satisfies a given specification. One common type of DNN property is reachability. Reachability properties define the post condition using constraints over output values, specifying that inputs from a given input region reach outputs within a given safe output region. For example, for the fashion MNES model, one possible specification could be that for all inputs, the difference of shapes between a t-shirt and an ankle boot has to be greater than the difference between a t-shirt and a pullover, being t-shirt the output class. Now let's move on to some of the challenges that DNN verification technique have. The first challenge is that currently verification focuses on the entire input space and wastes effort on inputs that are not relevant. For the case of MNES fashion, the images are 28 by 28 pixels, that is 784 pixels in total. Considering that each pixel can take values between 0 and 255, that will leave us 784 to the power of 255 possible images, which is a massive number, basically more combinations than atoms in the entire world. Nonetheless, according to the manifold hypothesis, real-world high-dimensional data lie on low-dimensional manifolds embedded within the high-dimensional space. Therefore, there is no need to explore the entire space, but the space where our data lies. The second challenge occurs when a verifier finds a property violation and outputs a counterexample. Depending on the specified property, if the input has no constraint, meaning that it can be any combination of pixels, then the counterexample will look like pure noise, and it is going to be far away from our distribution. The third challenge also takes place when a verifier produces a property violation. Under the same condition as before, if there are no inputs constrained, the counterexample is most likely to not be representative of the data. Consequently, it will be useless for developers to get an insight of what could be wrong with the DNN and what to do to fix it. So, what is our goal? We would like to make verification aware of the distribution of our data. And why do we want to do that? By making verification distribution aware, we will be focusing verification on relevant inputs. It will render property violations that are near our data distribution and thus better counterexamples. To address all the issues stated before and to meet our goal, we introduced DFB, an approach to make verification distribution aware. To do that, we need to focus on two aspects. First, we will need to characterize the distribution of our data, and then figure out how to make verifiers to consider that distribution. The machine learning community has been working on different techniques to model the data distribution. One of these techniques are generative models, which learn the distribution of the data and can produce new data by sampling from that distribution. Generative models are the secret sauce of our approach, since they will allow us to characterize the distribution of our data. More specifically, one type of generative models are variational autoencoders, also known as VAEs. A VAE has two big blocks, the encoder and the decoder. In general, VAEs can receive different types of inputs. However, for the sake of simplicity, I'm going to explain how it works with images. So, the VAE receives an image as an input. Then the encoder maps it to a lower dimensional representation structured by a Gaussian distribution of the data learned while training the VAE. And after having the latent space representation of the input image, the original image can be reconstructed by passing the representations through the decoder. Now that we know how to characterize the distribution, we need to figure out a way of making verifiers consider it. For that, we will need to update the DNN and also update the property. Let's start by updating the network that we want to verify. As I showed you before, the decoder block of the VAE is able to generate new image based on a sample from a Gaussian distribution in a lower dimensional space. Therefore, we are going to use it and append it in front of our DNN to create a new modified version of our original network. This new version of our DNN is no longer going to receive an image from our dataset as before. Instead, it's going to receive a latent space representation sampled from a Gaussian distribution. Then the decoder block is going to turn this representation into an image. And finally, the DNN block is going to predict that image and output the corresponding class. Now, since we updated the DNN that we want to verify, we will need to do the same with the property specification that we want to check. So, we have this safety property for the fashion MNES. That means for all inputs between 0 and 1, note that the range is between 0 and 1 because the pixels of the image are normalized. So for all inputs, the difference of shapes between a t-shirt and an ankle boot has to be greater than the difference between a t-shirt and a pullover, being t-shirt the output class. However, now the input of the DNN is no longer an image. Thus, we need to change the input of our property to match the input of the modified DNN. In order to do that, we are going to bound the input by using C standard deviations from the mean of the latent space Gaussian distribution, which is the input for the modified DNN. And this is going to be our outdated property. So to recap a little bit, we started by having a verifier that receives a regular safety property and a regular DNN. So in order to make verification distribution aware, we need to update the property to consider the new input boundaries, and update the original DNN to consider the data distribution by appending the decoder block of the VAE in front of it. So these are going to be the new inputs for our verifier, and it's going to output the same possible results as before. That the property holds, is violated, or unknown in case none of the first two can be determined. Now let's move on to the study section. Here, for time constraints, I will not be able to explain everything that we did, but if you want to learn more, feel free to check all the details in our paper. The first aspect that we wanted to assess was how effective is our approach DFB for falsification and verification. For that, we decided to use the fashion MNES dataset to train a model to predict different types of clothes. We designed 20 reachability properties, we implemented DFB using a variation autoencoder, and we ran 3 verifiers and 4 falsifiers. Another study that we did was to assess the scalability of DFB by using more complex models for more challenging inputs domain. For this study, we decided to use the DNN dataset since the images are bigger than the MNES fashion, and the model to predict the steering angle and probability of collision is more complex. We created 10 reachability properties for the DNN network. We implemented DFB using a variational autoencoder and a generative adversarial network, and we ran 1 falsifier. Before moving on to the results, I would like to make a short comment about how we measure the effectiveness of our approach. With effectiveness, we refer to a quality of a counterexample produced by the different tools. So how do we compute a metrics for quality? Well, we use the Structural Similarity Index measure, also known as SSIM, and for calculating it, we had to create a ground truth BAE. This ground truth BAE has the standard architecture of a BAE, but we use more layers and neurons than the BAE used for DFB. The input of this BAE is going to be the counterexample generated by the different tools, and the output is going to be a reconstruction of that counterexample. Intuitively, if the counterexample and the reconstruction of it are similar, the SSIM is going to be high, meaning that the counterexample is close to the data distribution. In contrast, if the images are different, then the SSIM is going to be low, and that will mean that the counterexample is away from our data. After that, we calculate the mean reconstruction similarity, MRS, by calculating SSIM between the original counterexample and the reconstructed counterexample for n amount of times and average them. Jumping to the results, we got this plot for the first setting. We can see, as indicated with the orange box, that all the tools are on the x-axis. From these tools, the first 4 are falsifiers. The last 3 are verifiers. On the y-axis, we have the mean reconstruction similarity that I just explained. Here is worth mentioning that higher values mean that the images are more similar, while lower values mean that the images compared are different. Each box plot represents the MRS scores for all the counterexamples found by each tool. The maximum possible number of counterexamples is 100, given by running 20 properties 5 times each. As you can see, for each tool there are 2 box plots. The blue ones represent the counterexamples generated while using DFB, and the red ones represent the counterexamples generated when using a regular DNN without DFB. The main takeaway here is that the MRS for the counterexample generated by using DFB are much higher than the ones generated by using a DNN alone. Thus, meaning that DFB is indeed making falsification and verification aware of the data distribution, since the produced counterexamples are much more closer to the dataset original image. So these are the counterexamples produced by different tools using regular DNNs without DFB. Now you may be wondering, what do the DFB counterexample look like? Here are a couple of images of what DFB generated. It can clearly be seen that the images on the left are pure noise or even black pixels, meaning almost nothing about the real distribution, while the images on the right definitely look like the clothes in FashionMNets. Now let me show you what we got for the other study that we assessed the scalability of our approach by using the DrawNet dataset. For this experiment, it's worth remembering that we only use one falsifier, the project rating descent. Let me quickly walk you through the plot. On the x-axis, we have 3 different models. The first one is the regular DrawNet model without DFB. The second model, BAE DrawNet, is a DrawNet model with DFB using a BAE in front of it. And the third one, GAN DrawNet, is the DrawNet model with DFB but using a GAN in front of it. On the y-axis, we have again the MRS. Higher values are better since it means that the counterexamples are closer to the real distribution of the dataset. The main takeaway here is that even though the BAE DrawNet model seems to have higher MRS than the GAN DrawNet model, they both have much higher MRS than the regular model without DFB, showing the potential of our tool to make verification and falsification distribution aware. Now let's see what the counterexamples look like. Again, we can see that the counterexamples produced by the regular network are random noise. The counterexamples produced by our approach with the BAE do not look as clear as the ones shown for the FashionMNets, but still much clearer than pure noise. For the 3 images, it seems that in each one of them there is a road and some bushes. If we look closer at the image in the center, we can see the back of a car or a truck. Lastly, here are the counterexamples produced by DFB with a GAN. Again, the 3 images show some sort of road and some trees or mountains. Furthermore, the GAN images look sharper than the ones produced by the BAE. So this is going to be the last section of my presentation, where I will talk about our conclusion. The first one is that by using DFB, we were able to make the verification and falsification process aware of the data distribution. Secondly, As I showed in the last slides, our approach produced meaningful counterexamples rather than pure noise. In third place, we tried DFV using BAEs with different settings, varying the amount of layers and neurons. By doing this, we realized that even simple generational models with few layers and neurons produce more realistic counterexamples. We built an artifact to replicate all the studies that we did, and it's publicly available at the GitHub repository of our lab. So if you are interested, feel free to check it out. This is the end of my presentation. Thanks for your attention. I hope you enjoy it and see you next time.